Hi, my name is Michael and thanks for watching this video. In this video, I want to talk about thermoelectric generators. These are devices that can convert heat into electricity. I have built one of these at home and I wanted to see if I could use them as a renewable energy source. I think I've got some interesting results along the way and I think I'm ready to share them in this video. So this would be my first YouTube video. I would really appreciate if you could leave me any feedbacks and comments below. So speaking of the generator here, what I have here is the generator that you would see in the video. In this video, you would see me using the sun itself as a heat source. So yeah, I guess you could think of this as a solar panel. But I found this device had some other perks. One of them, you would actually see me try to cook an egg on this panel. So I'm gonna call this name a TEG Teppanyaki because it does look like a flat grill itself, and it's kind of cool that you could use it to cook while you're out there cooking and generate electricity on the other times. So if you want to try and find out how I made this design and what happens with the grilled egg in the end, stay tuned and find out. So let's start with the very first question. Can we actually generate electricity using heat? I had the same concerns earlier, so let me show you this video here. This is the very first test that I've conducted. Back when I did this test, it was still winter, so snow were just lying around. I made this thermoelectric generator metal cup. I packed some snow around it, and watch what happens when I pour hot water into the cup. It works! So it works! See? So it can actually generate electricity using heat. I am very excited about this, and I can tell you why here. I have been waited for almost 20 years for this to work. Here's a little personal backstory. I can't recall exactly when. It might have been the last year of high schools, or maybe it's during the first year of university. But it was the time when I was learning thermocouple in class. You know, thermocouples? Those when you take two kind of metal wires, you twist them, tack them, and then you can make two joints. When you put one joint in the ice water bath for 0 degree reference, and for the other end, you can now start using it to measure temperature. The temperature difference between the two joints, they will generate a voltage and some kind of current. And by measuring the voltage there, you could actually calculate temperature. It generates voltage and current using heat. That sounds very familiar, right? So the story goes, I can't recall who said that. It might have even been a prof that mentioned it himself, but someone kind of asked the question, so can we actually generate electricity using these thermocouples? And the reason why I remember this very well is the prof never ever said no. Instead, he started to list the amount of energy this thermocouple could generate. We started to estimate, in order to generate a decent amount of electricity, how many of these couple wires do we need? And from then, what's the weight and how many wires? What's the cost of the material itself? So in the end, the conclusion we had was, it's not that it can't be done, it's just that it's not cost effective. And I remember this story very, very well because this is the very first time that I ever learned how cost itself can be a factor in the engineering design. I'm telling you this story because where I think this will be the key discussions throughout this video. I believe we can achieve anything here, but I'm looking for your help. Do you think what I'm trying to do here is cost effective or not? Do you see a future of what we're trying to achieve here? So later on, please leave a comment and help me out here. And by the way, not to mention, I waited 20 years for this technology to be around. So when I saw people started to make thermoelectric generators on YouTube, I kind of thought I had to be joining in as well. So that's how this project really started. So how does a thermoelectric generator work? I'll give you a very simplified example here. but I would recommend you to search up this term, future module, which is this little white tile here, because I do believe there are many others that can better explain this. And during my research, I was also trying to reference their videos instead. So please look it up. But now, if I could give a very simple explanation, I would go with this. Here's a DC motor, right? So for a DC motor to run, you have a battery source, you have a DC, you connect power to it, and you can see it spinning in one direction. If you reverse the polarities, now the motor would spin in the other way. What happened now if you connect the two what leads to the end and put a light bulb, for example, and you start spinning, you're spinning the motor, you now could generate electricity. So thermoelectric generators kind of work in the same fashion. These are future modules. If I connect it to the battery on one side, what's going to happen is you would have a hot side on the surface and a cold side on the bottom. Let's say it's a top and a bottom here. Now, if I reverse the polarity, it's actually going to switch. The hot side would become the bottom, and the cold side would become the top. So you can think of here future modules, they do not generate heat. They are more like a heat pump. They are moving heat from one side to another. And now, if you want to generate electricity, just like what we did on DC motors, instead of spinning the axle, you now need to apply heat to it with one side as hot and one side as cold. So that's just what happened in the video that I showed earlier. Now that we know how a thermoelectric generator works, let's talk about this project here. As I just mentioned earlier, to generate electricity, we will need a hot surface and a cold surface. Let me know if you've seen other videos, but when I did my little research, I noticed a lot of the thermoelectric generator projects were either using a candle flame or a firewood to heat the hot side. So basically, it was burning a fuel to generate electricity. Even in the video I've shown earlier, I was using a kettle to boil the water first to generate the heat. So I wanted to push this technology a step further. I wanted to ask the question, is there a way to use this as a renewable generator? And here's my thoughts here. If you look at your day-to-day temperature, you will notice there is always a daily high and a daily low temperature wave. If, and here's a big if I can draw this steady flat temperature line in the middle, that's where I think I can get the hot and cool temperature surfaces to run a generator. And when we factor in the sun, I think there is a bigger temperature delta that I could harvest. And that's what I've been building this thermoelectric generators based off. I believe this generator here, it is possible to generate electricity this way. Actually, I even did the test myself, so I know it will work. But the bigger question will be, do you think this is effective? So please take a look at these designs and let me know your thoughts. And to start, let's go through this design again. I'm going to play this video again. I'll speed up the video, and if this time you keep an eye on the voltage readout, take a look over here. And here is a picture of how it actually looks like. This is the very first prototype I built, and I'm very proud of it because you see, this experiment serves two very important milestones for the project. First, I also had my doubts if this technology is ready. So when I'm able to recreate this test myself, it's a proof that some of the videos you see on YouTube, they're actually real. And second, back to the is it cost effective question. Well, even though I know this will generate electricity, I had my doubt how much energy it could make. So the fact that it generated enough electricity, not just to light up the LED, but could also turn the motor, it really boosted my confidence in keeping this project moving forward. And now to talk about some improvements for prototype number one. Here's a picture I took right after the test. From the video, I'm not sure if you noticed how the voltage, while it skyrockets in the beginning, it's also dropping like a rock afterwards. That is, even though the water was still hot, and I still have all the snow around it. It appears that when the water melts away the ice, this snow is forming a bridge and doesn't want to come in contact with the filter module. So if I want to make any improvement for the next time, this might be the area I need to look at. And with that said, here comes prototype number two. Notice here, I wasn't just redesigning the thermoelectric generator. I'm not just redesigning this on the right, but I was also testing out various power meters that I can read out the voltage and currents passing through. Let me play you this first video. And once again, this is the hot rudder test. And now, right after hot water test, I'll play you this second video. This is immediately after I put it into ice bath. This is another important piece of the puzzle because this proves that thermoelectric generators, they don't just generate electricity by transmitting the heat outwards. If I do the reverse by absorbing the heat inwards, these generators could also generate electricity. And if I come back to this graph, this is the very important feature that I have to harvest the energy from the daily highs and the daily lows. So for prototype number two, I also tried leaving this outdoors, baking under the sun, but this is when things started to get silent or difficult because I've never seen the DC motor spin afterwards. It appears that the energy from the sun alone is not enough in this design to power up the motor. And so here comes the third prototype. The theme for prototype 3 was to test if water itself could be used as a heatsink. You see, for prototype number 2, when I just had only two metal plates stick together, it seems when one side heats up, the other side almost heats up immediately. And one side cools down, the other side seems to cool down right away. So what I need something as a buffer. I need something that could store the heat and keep one side of the temperature steady. So given that water has such a high heat capacity, this is my go-to for this prototype. I will first apologize here because what I'm about to say is you won't see any more videos from this experiment because it makes sense. Most of the time I'm just leaving this unit just sitting there. It's doing nothing. So all I have were just these pictures testing the units in various locations, various setup, and I even gave it this cover just to protect it from the rain. So I guess when I say this prototype works, I don't have any video evidence, but you might just have to trust me. But I would claim that this prototype works because this is my very first time I'm able to measure an electrical output that can be correlated with the sun. Now, the setup might not be convincing, so I also tried putting this water box inside the car because I guess you know how hot a car could get under the sun. During the day, the water inside the box will be heating up slower than the air that's trapped around the car. The water and air temperature difference, it generates a temperature phase delay. During the day, heat is being absorbed into the box. And here, which might not be clear, but I did document that we were reading around 0.87 volts out of this setup. And during the evening, when the car air cools down, the heat is now flowing outwards. And here I actually read a 1.15 voltage. Notice here I had flipped the polarities. This is how I know the direction of the heat transfer because I had to manually flip the polarity myself. And I had so much fun with this water box, but up to a point it started to become rusty and starting to leak. So it's again time to move on to the new design. Moving on to the fourth prototype, what I wanted to do was to flip the water box. I wanted the thermoelectric generators to be facing the sun and the water container will be underneath it instead. So the design goes like this. There will be a heat absorption plate on the top. The filter modules will be mounted underneath, protected by this top plate, and a watertight box will be constructed underneath the filter modules. The design sounds simple, right? But oh my, I didn't realize how much trouble I got myself into. Here is my first attempt, and you can see for yourself the problems I have. I started by going big with 72 modules. I didn't have a single plate that's big enough, so I thought I could just glue these plates together. And that is a bad idea. Water started to leak here, and things were starting to fall apart here. So very soon I went with trial number 2 and made it into a smaller unit. But once again I was just plagued with leakage problems, especially when I started turning on the water pump. The pump pressure seems to cause more leaks than I thought, so it's causing more leak here and here, and it caused a crack here, more leaks here and here. And eventually I finally found a compromise, and at least this allows me to continue and complete the experiment. But that is another reason why I'm ready to make this video. I feel like I've done enough with this particular experiment, and I'm ready to go back to the drawing board. But now, before I tear everything apart, at least let me show you what I've got so far. Before I show you the results, there's two things I should actually make note. First off, I'm not using the full panel as a thermoelectric generator here. The reason is there's actually damaged filter modules. It seems that as I've been moving and reusing the filter modules, I may have cracked and damaged a few. This actually is a very interesting defect here. It appears that the connection would break off only under heat, so pay attention to this hot water test. Take a look at this motor. Notice how the motor just suddenly stops spinning, even though I'm still pouring hot water onto the thermoelectric generator. This was a very interesting defect that I couldn't find out unless I really heated the generators. So there might only be one or two damaged filter modules inside this unit, but that's enough to cut away a good chunk of my modules. And in this data set presented, only 18 filter modules were used. The second thing you might want to be aware of is how I've been collecting the data. I've tested a handful of off-the-shelf DC power meters, but I can't seem to find one that satisfies what I'm looking for. So eventually I've built my own. Just so you're aware, everything that's south of this line is related to the power module that I've built. And yes, it is powered by a 5-volt power bus, but it is separate from the thermoelectric generator's circuitry. Down here, what you'll see, you would find a 5-volt and a 0-volt power bus. I'm using this to power the ESP32 controllers. The ESP32 comes with Wi-Fi connection, so I am also logging the local weather station's temperature, cloud coverage, and rainfall, etc. from the weather station. As for temperatures, I am using DS18B20 temperature probes. And the most important feature of this test is actually this micro SD card. This is actually the most important feature because it allows me to run the experiment for days and days and days without standing by and logging data every single time. And now up here, what you have here is the thermoelectric generator circuit. What I am using is an INA219. This is used to log the voltage, current, and power of the thermoelectric generator. The thermoelectric generator comes in on the right side here. The DC motor will be the given load. There's also some LEDs here which tells me which direction of voltage or current travel this thermoelectric generator is making. So finally, let's start talking about the test results. This thermoelectric generator project, there are three different modes it could run off. I'm naming these modes static mode, the pump mode, and a quench mode. I have tried these different modes in separate times before, but for this final test, I really wanted all the test data to be done in close proximity. So you can see, down here, these are the dates when these tests were performed. I really wanted them to be tested on dates that are close to each other so that the seasons or the weather impact would have a less of a factor on the data. Starting with static mode, this is how I set up the test. Like said, this is quite boring because you're not going to see much action here because I've just left this just sitting outside and baking under the sun. And for the data I collected, this is what you'll see. What you have here, all these colored dots, these are the readings from the temperature probe. And what you have up here for these gray dots, this is the power output from that power module. Some interesting observations here. The higher the temperature doesn't necessarily mean the higher the power output. And I'm going to explain that later. So let's just pick this date here, just because this has the highest power output. Now that I zoom in the chart, I'm able to plot a lot more samples and a lot more details here. A couple things I should first explain. Temperature sensor 1, that's the sensor that I put inside the thermoelectric generator. Temperature sensor 2, that's the sensor that I put on top, that's just being taped on top of the thermoelectric generator. Temperature sensor 3, this little green line here, it's meant to be tucked underneath so that it's protected from the sun. It's meant to be measuring the ambient temperature. Temperature sensor 4, that's the temperature sensor that's placed inside the water reservoir. And all four of these temperature sensors uses the main axis on the left, and the units are in degrees Celsius. Whereas the calculated power, this little gray line on the top, they are being plotted based on the line on the right, and the units are in milliwatts. So a few observations I like to point out from this chart. The time that I started this plot is from noon to 7. Now the reason I've done that is because of the site location I picked. Before noon, the sun is being blocked. The thermoelectric generator doesn't have any direct sunlight. That's the reason why all the energy generation typically happens after at around 1 o'clock when the sun starts to strike. And the second observation, as a renewable generator, you can see I am definitely getting some kind of energy output. It's not a lot, but I do have some. And they do somewhat match kind of the peaks that you see up here. And from here, what I could find, I have a peak power output of 0.05 milliwatt. And following that line below, that's roughly a 16 degrees temperature delta. Another observation I see here is from 4 o'clock to 6 o'clock. Somehow this temperature just dipped down. This is an interesting phenomenon. I believe there may have been a cloud coverage just happened here. So you could see the top metal kind of just drop down and kind of merge to the ambient temperature and match the ambient temperature line. So from here, what you can see, the key here is this yellow line. This represents the flat line that I'm trying to grab from the weather chart. Because this thermoelectric generator is leaking, this yellow line represents air that's being the heat medium inside the thermoelectric generator. And what could you see here? To generate energy, what you're looking for is a large temperature delta between the light blue and the yellow line. And that might explain on these days, even though the temperature was a lot higher, notice how the yellow line kind of shoots up and follows close to each other. That might be the reason why you're not really generating a lot of energy on these days. What I should point out though, after 1, 2, 3, 4, 5 days of testing, I could only generate a maximum of 0.05 millimeter watts. The LEDs were having a very faint light, but the DC motor never spin. So what do you think? Is static mode even reasonable? So let's move on to the next mode, the pump mode. And this is how the mode runs. And from the test, this is what I get from the data. Because the pump uses a battery, it's not like I've been running the pump 24/7.
There are only certain time slots throughout the day that I'm running the pump. But right away, what you could see, there's a huge difference that's compared between the static mode and the pump mode. And let's zoom into this first date here, given that it has the greatest power. So on June 29th at around 1 p.m., that's when I ran this pump test. And that's where I had the greatest amount of power output. You could see it's quite a significant improvement. A whopping 3.5 milliwatt peak power was generated. And roughly, I would say over time, it might be around zero point 0.4 milliwatt during a steady state. Some observations I want to mention here. I do have gaps in my data sometimes. That's when the ESP32 disconnects from the internet. I hope you could ignore this portion here. I'm very glad it actually turned on right before I started my pump tests. This line here demonstrates when I first turned on the test, and you can see this is where it get the greatest thermal shock. Right here, the thermal temperature of 30 degrees temperature delta, that generated the most amount of energy. I had a 3.5 milliwatt peak. Some interesting observations here. Notice how this yellow line and the dark blue line, they merge and follow very close during these areas. This is the time when the pump is running. And I could even see here, this is when the battery ran out and the pump stopped running. This is when the separation starts again. And another interesting observation, notice how this light blue line drops in temperature right away. It makes a lot of sense since the water is taking the heat away from the top surface. Somehow this behavior makes me wonder, what about all the complaints about a scorching heat on the pavements or sidewalks? Is there something here that I could be done? Could I use those unwanted heat on the sidewalks to heat this thermoelectric generator? So what can I conclude for the pump mode? I'll say this. It's definitely generating more power than the static mode. But while I don't have any video evidence, my observation here is the LEDs were a lot brighter, but the DC motor didn't run either. So given that I had to use a battery to power on this pump, I have a feeling that the power output that I generate from this thermoelectric generator is not equivalent to the power input that I use to run the pump. So now moving on to the quench mode test. And what do I mean by the quench mode? This is what I meant. This is the favorite mode of all time because I was pouring hot water right onto the thermoelectric generator. And then immediately I would follow by a water bath. It reminds me of a blacksmith quenching a sword, so I'm calling this the quench mode. And what did I capture during the quench mode? And again, these are the 2 days that I tried the test setup. And let me take a look and zoom in onto this day. Now, because this mode happens so fast, you can see here how the sample frequency of my power module is starting to look not enough data points. But at least you could see the shape here. You can see this is the time when the hot water was poured, and it only lasted about 2 minutes. You could see here the light blue line kind of shoots up. Maybe this is around 90 degrees Celsius, where all the other temperature probes, they really don't have much time to react. This is where we get the most power. I'm getting a whopping 613 milliwatts. And a breakdown of that, it's 10.5 volts and 58.4 milliamp. And this is kind of the steady state here. When I was pouring the water around, I would say it might be around 550 milliwatt is my steady state output. You can see from the video, the LED is definitely very bright and the motor itself also spins. Now, one note to point out, you notice that I don't have any measurement for the cold side. It's more of because the power for some reason is only measuring zero. And and it's not meant to. It's not meant to do so because from the video you could definitely see the blue LED does come on. So it might be something in the circuitry that I have to review. Perhaps it's because how I connected the loads together, because I only have a single load, and when a TEG flips its polarities, the INA219, it couldn't read negative voltage. So it calculates a zero power output. but further experiments will be required. Regardless, even if we just focus on the hot water test, this reference here of 613 milliwatt might be sufficient for us to carry on. And this would be the summary that summarized our results. Few things to point out. It's not surprising that the greater our temperature differences is, the more power we generate. And the power to temperature difference, it's not just a linear growth, but it's more like an exponential growth. I will consider here that the static mode and the pump mode are renewable energy harvesting modes. Quench mode is where I had to use a separate fuel to heat up the water. So I feel like this comes back to the key question I've been asking. Can a thermoelectric generator operate in a renewable energy mode? I think it can. But the question then is, does it worth it? Is the power output cost effective? What do you think? Now, wait. Don't turn away yet. I'm not done. I did mention this generator had some perks, right? Remember, instead of generating electricity, these future modules, they can be used to move heat around. I can generate a hot surface or a cold surface whenever I want. And this is how I did the setup tests. So when I was designing this generator, I purposely left the leads exposed. The thinking here is I would later design a series to parallel switch, and I could quickly switch it from series to parallel and give it power. Over here, I have 20 rechargeable batteries. They are NIMH rechargeable batteries, and I had 20 of them because that's really all I can find in the household. It's not that I don't want more. Anyways, if I put these together, that would be around 24 volts that I'm using to power these filter modules. And during this test, I would have a thermal camera to record what's happening, and I would have the pump running. And if you had such a good eyes, please ignore this egg for the time being. You'll find out what happened very soon. So here's what you see under a thermal camera image. I've been running the water pump already, so it reached steady state. The starting temperature of the plate seems to be steady at 28.8 degrees Celsius. When I first connected the wires, I guess I had the polarities wrong. It was started by heat up mode. You can see how the units were heating up first. Then you could see me flipping the battery polarities, so the filter module is in cool mode. And see how the surface cools down immediately. So give it some time. You see the coolest temperature it could reach seems to be at 11.8 degrees. So it dropped by 17 degrees temperature delta. And now I'm going to flip the polarity and change it into heat mode once again. See how it heats up. I guess it's around steady state here. It's approximately 61 or 63 degrees Celsius. And oh, okay, for crying out loud, I I plead guilty. I did wanted to cook an egg right away, and here's what happened. I killed an egg by letting it slide off the slope. Oopsies. And now this is where it got me thinking. Could I actually cook an egg on this thermoelectric generator? Well, 60 degrees Celsius isn't hot enough to cook an egg, but there are several options I could think of. One, I could actually find more battery and give it more power. Or two, I could actually preheat the water so the baseline is actually closer to boiling point. There are several ways I could preheat the water. When I was first designing this box, my initial thought was to put this heat cartridge from a thermal printer inside the thermoelectric generator. But given that I have so much problem with the water box, I kind of picked the easier and cheaper way, which I'll just boil the water before I run the test. Well, and here goes trial number 2. Oh no, the egg drop again. Trial 3. Better, but it dropped again. So in the end, I decided to find some scrap core rolls, and I cut myself this little egg ring. And take a look at this final trial. So for this test, I connected the 20 batteries over only 3 filter modules, giving it 6 volts instead of 4. And notice here I purposely offset the ring. I wanted to prove out it's the filter module that's generating the heat and cooking the egg, not the hot water itself. And see how the egg white changed color and getting cooked already. Everything seems to work well in the very beginning. It seems like I am cooking the egg right away. But very soon I notice I am having no reaction for quite a while. Let me speed up this video here. Very soon I see no more cooking action and I kind of gave up after 30 minutes. I did some cleanup and I felt disappointed. But this is what I thought. I thought of doing this one more hot water test just to find out what's happening and, well, what you know, I actually burnt and damaged the filter module. I guess that's why the egg weren't cooking anymore. So the two takeaways I see from the test. 24 volts over 3 filter module is too much. It will damage the module, so I have to do some optimization there. And two, I still believe that if I didn't burn the module, I would have cooked the egg, and I could officially call this a TEG Teppanyaki.
I hope you've enjoyed this video so far. Thanks for watching. What are your thoughts? How do you think about thermoelectric generators? Do you think it's a project still worth moving forward on? You see, I am ready to go back to the drawing board, but I will want your inputs into what I should do next. I have actually thought of 3 different directions I can move this project forward. But before reviewing them, I want to ask you this. I want to ask you, could you actually pause this video for a moment and write down your own ideas? Maybe there is a fourth brilliant idea that you have, and I will really like it if you could share that thought with me. So if you can, please give this video a pause now. Okay, have you wrote down your thoughts already? Are you ready? Okay, here it goes.
So for option number one, I'll head back to the summary chart here. After all the effort I put in, I am only able to generate half a watt. Do you think half a watt of energy is efficient or not? So maybe generating electricity using a fuel isn't a bad option. So if that's the case, my thought is, should I continue on and improve the TEG Teppanyaki design? What I had in mind is I would take this TEG Teppanyaki, I would take this pump, and I would take this fire stove. So the idea will be, I would treat this as a portable grill. You could take this for a camp. During use, you would have a heat mode that you could cook and grill food on. There will be a cool mode that I'm thinking it would be treated like an ice lug, so you could cool down your drinks in the wilderness. And when you start up a campfire, you would change it to the generator mode, and that's when you would charge your phone, power bank, and enjoy the fire camp as you're doing so. Now, for option number two, I would still want to focus the thermoelectric generator as a renewable energy mode. And I think out of all the energy made, the water pump mode makes the most sense. So option number two is to focus on the water pump mode and see how I could find improvements here. What I'm thinking is I might even make this into a sculpture instead of a flat plate with a water fountain underneath. Not just it could generate electricity, it has the water fountain as the heat reservoir, and it might even be a piece of public art. And as for option three, what if I ask you, maybe energy harvesting is not the main theme? What if I only focus on the perks to generate heat? Here I live in Canada and it snows during the winter, but where I live, it doesn't snow frequent enough. So if I want to install a heated driveway, it kind of feels like a waste of money because it's not really used most of the time. It might be used in a couple of days during a few months, but that's really it. Most of the time, it just sits there. What if I tweak the question and say, what if the heated driveway is made of these thermoelectric generators? So during the winter, that's the only time we'll heat up and melt away the snow. And during spring, summer, and fall, maybe it doesn't generate a lot of electricity. It's still better than none, right? What is your thoughts on this? Thank you for watching this video, and that's all I have. I hope you enjoyed watching this today, and if you have any thoughts, please really leave me a comment below. I'll be looking forward to it. And because how YouTube works, if you could also subscribe to this channel, this would help me a lot. And thanks for watching.